If I want to take the derivative of two functions divided by each other, is it just the derivative of the top over the derivative of the bottom? The answer is going to turn out to be a no. And you can show this just by a simple example. So for instance, if I were to say, take the derivative of x squared over x squared, this would be the same as saying take the derivative of 1, which would be a 0. But if I were to use this phony baloney quotient rule, I would have to take the derivative of the top over the derivative of the bottom. So that would be 2x over 2x, which would be 1. So clearly, 0 doesn't equal 1. Well, what is the right rule? And just like before, we need to go to the definition of a derivative to come up with the correct result. The thing inside the bracket here is what we will consider to be our function. So the definition of the derivative says, take the thing in the purple box, plug it in at x plus h, subtract the thing in the purple box at x, and then divide the whole mess by h. Just like before, 0 over 0, and no limit laws are possible. Or we need to do some algebra. Now, I won't do the algebra this time, but I'll walk you through what should happen. So what you should do is use a common denominator, and then you're going to add in a 0 like we did last time. Now again, you're not going to be putting in this symbol, big fat 0. Instead, you're going to do some algebraic expression that will help you get more terms to play with. And so through trial and error, the right expression will be this. Now there's another version, but this will suffice. And again, we are assuming that f and g are differentiable. And what happens is that this leads to what's called the quotient rule. And the quotient rule is the following. So if you were to take the derivative of a quotient, a function on the top over the one on the bottom, turns out to be f prime times g, so the derivative of the top times the bottom, subtract f times g prime, all over the bottom function squared. This time, the order of f and g does matter. Remember that if you were to have a fraction, you can't flip-flop the top and the bottom to get the same number. 3 over 5 is not the same as 5 over 3. So similarly, you wouldn't expect the derivative of a quotient to allow you to flip-flop those either. And in fact, it doesn't. The minus sign upstairs doesn't allow you to flip-flop them and keep the same number. And the g in the bottom also says you have to pay attention to what is what. The quotient rule turns out to be very straightforward to use as well. With the quotient rule, this becomes really simple to do. So the only thing that we really need to remember is what's f and what's g. So the quotient rule says take the derivative of the top function multiplied with the bottom, subtract the top function multiplied with the derivative of the bottom, all over the bottom function squared. The derivative of x squared plus 1, you can use the linearity rule. It's going to be 2x plus 0, so all we need right is 2x. So we'll get 2x times x minus 2, subtract x squared plus 1. The derivative of x minus 2 just ends up being a 1. Now, just like before, we want to distribute everything to try to clean up the result as much as possible. X squared minus 4x minus 1, x minus 2. And it's as simple as that to get us to the result we want. The quotient rule allows us to extend the power rule to negative exponents. Now, at last class, we said that the power rule applies to all real numbers upstairs in the exponent, but the proof that we did only allowed us to use integers. 1, 2, 3, 4, 5, 6. So the quotient rule allows us to extend that proof. And it says, you know what? If you ever have x to the power of m, you could treat it as 1 over x to the m, and then use the quotient rule from there, and you'll be able to get a result that matches with the power rule.